So far, our discussion about probabilistic modeling has focused on one variable at a time. What's the distribution of the number of sales a telemarketer is going to make? What's the distribution of the amount of money that someone is going to spend the next time they visit a store? But very often, especially in business analytics, we're more interested in looking at the probability of combinations of random quantities. So, for example, with the telemarketer example, what's the probability that the telemarketer would make between 90 and 110 calls while having at most, say, 30 sales? So two or more random quantities, and our question about the probability involves both of them simultaneously. Now, where I think that really comes into play is thinking back to our refinery example, where we were trying to inject a bit of realism into the linear program that was designed to figure out how many barrels of gasoline versus crude oil the refinery was going to be produced, where we tried to model the uncertainty in the profit that we would get per barrel and the refinery capacity, the demands, and also the fleet capacity. And in our investigation, what we did is we came up with distributions to randomly pick what the profit was going to be due to a barrel of gasoline, the profit due to a barrel of crude oil. But we knew that there was actually a relationship between those two random quantities, the prices that we could get from the crude oil and the gasoline. Looking at a scatter plot, we saw that they had a positive association. Larger values of one quantity were typically found with larger values of the other. If we were to look at some sort of contour plot, we see the same sort of pattern. Clearly, there's some sort of an association between them. So our simulation was a bit incomplete and unrealistic because we were picking the prices independently of one another. We picked the price for a barrel of gasoline completely independent of the price that we might see for the barrel of crude oil. And if we want to have a more complete understanding of the possibilities we might run into in the future, we would like to respect this sort of association. So we'd like to figure out some way to model the combination of values for the price of gasoline and the price of oil. And really, this is going to crop up a lot in business analytics. Besides the telemarketer example, we might have a question about the lifetime value of customers. So when we did a simulation about lifetime value, we simulated the number of years that a customer was with the company separately from the number of times the customer was going to make a purchase per year, which was also separate from the total amount spent per purchase. And we can imagine that there's probably some sort of relationship between these quantities. The more times that people are purchasing from a company per year, maybe the less amount they're actually going to spend on each instance. Or another example, if you're working for a charity and you're studying people's donation amounts, well, it stands to reason that people's donation amounts this year are probably related to the donation amounts last year. So your question might be about the combination of the amounts of money people have donated in both of those years, and there's likely going to be a pretty strong association. Maybe it's the case that people are either consistent donors or really not very consistent at all. So if they donated a lot last year, maybe they're more likely to donate a lot this year. Or maybe there's a separate pocket of customers that kind of alternate. Maybe customers that donated a lot last year are more likely to not really donate much this year among a certain segment. So a lot of questions in business analytics really boil down to questions about combinations of parameters. And so what sort of probabilistic models can we use to describe combinations of values? So a bit of terminology. When we do talk about the probability of combinations of random quantities, we're going to be talking about the joint distribution of those two random variables. So the joint distribution of gas and oil prices, the joint distribution of last year's donation amounts and this year's donation amounts, the joint distribution of the number of years the customer continues shopping with the number of times per year and the amount spent per visit. Now, we can actually derive the joint distribution if we stay within the context of hierarchical modeling, actually really quite easy. And we can just take a page back from our classic rules about probability, where we wrote down the multiplication rule for the probability of two events, A and B, both occurring. We wrote that as the probability of A given B times the probability of B occurring. And so we see if we work within the hierarchical model framework, recovering the joint distribution is simply as easy as just multiplying our formula for the conditional distribution times the distribution of that random parameter. So if I wanted to know, well, what is the joint distribution of the number of calls and the number of sales that a telemarketer might make? Well, I can take that binomial conditional distribution of the number of sales given a particular number of successes times the probability distribution we've ascribed to the random number of calls, that Poisson random variable. Easy enough. And when we do that, we can look to see what does the probability distribution look like, what combinations of values are more likely than others. This contour plot is showing the joint distribution of the number of calls and the number of sales. We can see that it's peaking at about 100 calls and 20 sales, which if you remember, 100 was the average number of calls. The probability of a successful sale was 20%, so this makes sense. And it looks like a tilted ellipse or something like that. Gives us an idea of what combinations are more likely versus less likely. So in the context of a hierarchical model, really no problem coming up with the joint distribution, multiplying that conditional distribution times the distribution of that random parameter. We had that example with the log normal amount of money that people were spending given some parameter for the mu of the log normal, but that mu parameter was distributed as an exponential distribution. If we wanted the joint distribution of both of those quantities, all we had to do was multiply those two formulas together. And I think if we're going to study combinations of random variables, it's best to do this in the context of the hierarchical model, because otherwise it's extraordinarily difficult to actually come up with an equation that really describes the probability of various combinations adequately. This is just a very difficult thing to do. So just to give you an idea of how difficult, in general, even modeling two random quantities can be, let's imagine that you find the following shape to be appealing. Basically, this is the properties of the joint distribution that you would like to have. Values of x1 of 6 and x2 of 6 kind of are the most likely, say overall it reaches a peak there. And there's a secondary peak at maybe around x1 of 3 and an x2 of 3. If we were to look at a 3D dimensional plot of the joint distribution, we would find something that is nice and bimodal, but good luck just sitting down and actually coming up with a formula that actually produces this shape. And this is why modeling joint distributions is a very difficult thing for us to do. It's very difficult to propose a shape, find an equation for a shape that we like, and then convert that into a valid PDF. This is much easier to do inside of that hierarchical modeling framework. So if you open up a textbook or you do much research online about joint distributions, most of the time what's going to happen is you're going to be thrown some kind of weird looking formula that just kind of materializes out of thin air that really doesn't have much correspondence with anything that we would observe in reality. So for example, maybe we'd have that the formula for the joint distribution of two random quantities, x1 and x2, is 12/7 times x1 times the quantity x1 plus x2. Both x1 and x2 have to be between 0 and 1. If we talk about the probability of combinations of random values, we could use that as the joint PDF. We could answer questions about probabilities of finding values inside of a certain range, expected values, etc. But the discussion really lacks significance because what real-world phenomenon is really going to have combinations of values that are described by this quantity? If we were to go and just look at a plot of what this joint distribution looks like, we would find that larger values of both x1 and x2 are a bit more likely than smaller values of little x1 and x2. We could make a 3D plot of the density as well. And exploring that, we can kind of see what values are more likely than others, what combinations are more likely than others. But once again, what pair of real-world quantities would really have this distribution? I'm not really too sure. And so a lot of discussion you find in the textbooks online are these very artificial discussions where they've just proposed some sort of formula for the joint distribution, just ad hoc, just to have something to play around with. So, to reiterate, working with joint distributions is actually really difficult to do. Number one, because developing a realistic formula that talks about the probabilities of finding various combinations extraordinarily difficult to do outside the context of a hierarchical model. And number two, once we do start talking about probabilities with joint distributions, probabilities of finding various combinations, that requires us to really work with multivariable calculus, multidimensional integrals, and that's something that most of us really aren't all that comfortable doing. If we stay inside the framework of a hierarchical model, number one, not only is it really easy to actually come up with that formula for a joint distribution, but it's also very easy to simulate. And then we can just ask questions about probabilities of finding various combinations via a Monte Carlo simulation. So once we have our formula for the joint PDF or PMF of our random quantities, what sort of questions might interest us? So, for example, with that telemarketer example, we might want to know what's the probability of observing 90 to 100 calls and between 10 and 20 successes, a question about both those random quantities at the same time. Well, in this case, since both of these quantities are discrete, what we can do is something very similar to what we did in just the one variable case. If we want to know the probability of some event of interest, we just sum up the probabilities of all events that meet our condition. In this case, we just need to make sure that we sum up over all combinations of quantities that meet our event of interest. So this will require, in general, a for loop or integration if they're continuous quantities. But we can go and sums over the joint probabilities of all the combinations of interest to us. And for our question, we find that there's about a 25% or so of having the telemarketer have between 90 and 100 calls while having between 10 and 20 successes. We could ask another question, well, what's the probability that the number of sales is, say, less than 15% of the number of calls? Remember, each call has a 20% chance of being successful, so that seems to be relatively unlucky. All we have to do is write our for loop, go through all the possible combinations that satisfy our event of interest, and sum up the probabilities of those combinations. Not too bad just talking about it in English, really, but once you try to translate that into some sort of operational definition inside of a for loop, it can get a little bit tricky figuring out how to flesh out the combinations of those values that meet your event of interest. Now, what would we do, say, if our random quantities are continuous instead of discrete, like the log normal spending example, where the amount spent is log normal given some mu parameter, but the mu parameter is anywhere that's described by an exponential distribution bigger than 0 here? Well, something similar to what we would do if asking a probability about a continuous random variable. If we wanted to know the probability of getting a value of x, say between 3 and 5, we just take the area underneath the curve between x equal to 3 and x equal to 5 for the shape of the PDF that we're working with. And when we're talking about more than one random variable, a joint distribution, it logically extends, except for instead of calculating the area underneath some sort of curve, we're going to be calculating the volume underneath some sort of surface. And so calculating volumes underneath the surface requires multivariable calculus. It's been a while since we have actually done that. And so if we have to do that mathematically, that's going to be a difficult thing for us to do. Luckily, Wolfram Alpha is going to be there, but it requires some pretty advanced math. So in general, how would I actually write that down? Figuring out the probability of finding, say, x1, my first random quantity inside of a range a and b, and my second random quantity x2 inside of a different range between c and d. Well, that would be the double integral of my formula for the joint PDF, where I'm varying x1 over that range a to b and x2 over that range c to d. So it becomes that volume of the space underneath the surface described by the curve of my joint PDF. And so if we really wanted to do this, we'd have to review all of our rules about multivariable calculus. I don't think that's very productive because for the most part, we're going to be working with hierarchical models that allow us to simulate quantities very easily and just ask questions with a Monte Carlo simulation. But the key thing is that if you really want to do this, the tools are there. For that very artificial PDF that we proposed at the beginning of this discussion, we can go and make a plot of that PDF looks like 12 times x1 plus x2, where x1 ranges between 0 and 1, x2 ranges between 0 and 1 here as well. We have a little idea of what that surface looks like from Wolfram alpha. And if we wanted to go and figure out the probability of finding a combination inside of some sort of range, well, it would be some sort of double integral. Wolfram alpha can handle that without too much of a problem. Not sure it's a great use of our time, though, in this class. Similar to what we'd see in the one variable situation, when we go and want to calculate expected values of functions, etc., the formulas look very similar when we have a joint distribution. The expected value of, say, x1 would just be x1 times our formula for the joint PDF, integrated over all possible combinations of x1 and x2. If I want the expected value of some function, and maybe that function involves both x1 and x2, I would transcribe the formula for that function, multiply that by my formula for the joint PDF, and then integrate over all combinations of x1 and x2. So the math is there, but in my opinion, it's usually going to be easier to answer some of these questions with Monte Carlo simulation, mostly because actually having a formula for that joint PDF is usually out of reach, unless we're working within the context of a hierarchical model, in which case simulating is just so much easier. So when it comes to discussing multivariate distributions that involve two or more variables, here's some key terminology bits that we're going to want to be well familiar with. Words that we've heard before, but it's good to review them and put them in the context of dealing with multivariate distributions. So, number one, we talk about the joint distribution of the combination of random variables by talking about some sort of formula that gives us the probability of observing a certain combination of those random quantities. So, the joint distribution talks about how those quantities vary jointly. If we're interested in just one of those variables, like x1 or just x2 all by itself, well, we can get the marginal distribution from the joint distribution, actually just by summing over all of the values of the random variables that don't interest us, or by integrating over all the possible values of those variables that don't interest us as well. But the marginal distribution is just the distribution of one of the variables all by itself. We also might be interested in the conditional distribution of one of those variables for a particular value of the other. And we've been working with this with hierarchical models. That conditional distribution of the number of sales, given the number of calls was binomial, the conditional distribution just talks about, well, what does the distribution of one variable look like for a particular value of that other variable? And we can actually develop formulas that allow us to go from one to the other, just by using our old classic formulas in probability, namely that multiplication rule that the probability of two events, A and B, works out to be the probability of A given B times the probability of B, the conditional distribution of A given B times the marginal distribution of B, or vice versa, the conditional distribution of B given A times the marginal distribution of A. And the nice thing is that these formulas just extend nicely to the world of working with PMFs or PDFs here. So if I want to know the joint distribution of two random variables, x1 and x2, well, as long as I know the conditional distribution of one of them and then the marginal distribution of the other, I could just multiply those two together to get the joint distribution. This is what we've been doing with hierarchical models. If instead I wanted to get the marginal distribution, say from the joint distribution of the combinations of those random variables, well, I'm just going to integrate over or sum over all the possible values of the other random variables that I'm not interested in. So formulaically, if I wanted to know the marginal distribution of just x1, I can take that joint distribution, the combinations of x1 and x2, and just integrate out x2. Integrate over all possible values of x2. If it was discrete, I would be taking the sum over all the possible values of x2. So with that rather generic, artificial-looking joint distribution of 12/7 times x1 plus x2, if I just wanted to know, well, what's the marginal distribution of x1 alone, I can take that formula and then integrate out x2, integrate over the range of possible values that x2 can make, which is between 0 and 1 in this case, and I recover some sort of formula. Now, if we are working in that rather artificial context of having a formula for the joint distribution, we can actually recover the conditional distribution of 1 with just a little bit of math. All we really have to do is take the marginal distribution for one of them, look at the joint distribution of both, and do a quick little division. So, for example, if I wanted to know, well, what is the PDF of x1 for a particular value of x2? Easy, just take the joint distribution of both random variables and divide by the marginal distribution of x2. This is just like P of A given B is equal to the probability of both occurring divided by the probability of the event on which we're conditioning. The same probability rules just extend naturally to when we're talking about PDFs or PMFs. And so this is really why we like hierarchical modeling so much, because in that hierarchical model, we have the conditional distribution of x1 given x2, and then a distribution of x2 as well. So we can get the joint distribution of both those random quantities by multiplying those two formulas together, and that allows us to calculate expected values, probabilities, really quite easily. Especially if we're willing to just Monte Carlo it, have that two-stage process where we generate a random value for that random parameter, then generate a value for that quantity of interest. That provides really a nice, tidy method of answering any sort of probabilities that we'd be really interested in pursuing. So thinking back to that telemarketer example, we had that hierarchy. The number of sales given the number of calls was a binomial distribution with parameters n and p, but n we were going to treat as a random variable. It might vary from day to day. N is going to have the distribution of the Poisson random variable with a parameter lambda. So we have a conditional distribution, we have a marginal distribution, the marginal distribution of our random quantity. Multiply those two together, and out comes the formula for the joint distribution of the combination of both values simultaneously. If we were going to make a plot of that joint distribution, we could do so. It looks like a tilted ellipse, but it lets us know what combinations are more likely, what combinations are less likely. And so we can see that the peak of this distribution really is having a number of calls of 100, the average of that Poisson, and the number of sales of 20. Basically, the chance of success for each call times that average number of calls. If we wanted the marginal distribution of just the number of sales, well, we can just take the sum over all the possible values for the number of calls with that joint distribution of the combinations to figure out, well, what's the distribution of the number of sales alone. We did this last time. We asked Wolfram Alpha to help us out with that sum, and we came up with that discovery that the distribution of the number of sales after we free itself from the dependence on that random number of calls was actually a Poisson distribution with the parameter equal to lambda, the average describing the distribution of the number of calls itself, times p, the probability that each call would result in a sale. Now, our discussion of joint distributions really simplifies if it happens to be the case that the random variables are independent of one another. And we've talked about independent events before. If I have, let's say, a fair coin in one hand, a die in the other hand, and I want to ask the question, well, what's the probability that I get a heads and a 1? Well, since the outcomes of those two events are independent of one another, I just got to straight up multiply the probabilities of the component events that went into my question. So the probability of heads times the probability of rolling a 1. We've talked about the probability that a batter would be struck out if the outcome of each pitch was independent. If we wanted specifically the sequence, 3 balls followed by 3 strikes, basically a combination of 6 different events there. First ball that's pitched is a ball, second's a ball, third's a ball, fourth's a strike, fifth's a strike, sixth is a strike. If each of those are going to be independent, we just straight up multiply the probabilities of those component events to get the probability of a ball to the third power times the probability of a strike to the third power. And if I was going to look, let's say, at the combination of people's heights in a class, so if our class has 40 different people, 40 different random variables, the combinations of heights that I might observe, those values are probably going to be independent of one another. Your height's going to be independent from the height of the other people in the class. I could just multiply together the probability distributions of just the distribution of height in general. So, if it happens to be the case that we're dealing with a combination of independent events, if I have the question, well, what is the joint distribution of that collection of random quantities? Very easy. I can immediately write down a formula for that. It's just going to be the probability distributions of each one of those random quantities multiplied by each other. So specifically the joint distribution of x1 and x2, if both x1 and x2 are independent, it's just the PDF of x1 times the PDF of x2. And if x1 and x2 are independent, well, the conditional distributions simplify to just the marginal distributions themselves, because there is no dependence between the two. The conditional distribution of x1 for a particular value of x2 is just going to be the marginal distribution of x1 because x2 doesn't have any sort of bearing over what possible values of x1 that we might end up observing. Now, it comes as no surprise, though, that in business analytics, most things worth studying are not going to be independent. The random quantities will have some sort of an association, and our job is to try to capture that association as accurately as possible. So the price of oil and the price of gas, we know there's going to be an association. We want to capture what that relationship looks like. The amount that someone gives to charity this year versus last year. Clearly there is going to be an association. What does that association look like? When we are dealing with two events that are not independent, we want to quantify just how strong of an association there is between them. So how can we do that? How can we summarize the strength of an association between two random quantities? Well, one way to do this is by calculating the covariance or the correlation between the two random variables. Now, formulaically, all the covariance is going to be is the expected value of a very particular function of both random variables. So to get the expected value of some sort of function, we take our formula for our function of interest. In this case, for the covariance, our function is going to be the product of the difference between the x1 value and the average value of x1 times the x2 value minus the average value of x2. That particular function is what we want to get the expected value of. So we take that formula, multiply it by the joint PDF, and integrate over all the possible combinations of values we might see. Or take the sum if we're talking about discrete quantities. So what does this formula really do? Well, if we inspect it really closely, it actually tells us something fairly interesting. So one thing we see is that it's comparing the value of x1 to its average and the value of x2 to its average. So if it's the case that above average values of x1 are typically found with above average values of x2, well, that function is going to be positive. Positive times a positive is a positive. And likewise, if below average values of x1 are typically found with below average values of x2, well, negative times a negative is a positive as well. So if we have a positive association where larger values of one quantity typically are found with larger values of the other, the value of that covariance is going to be a positive number. And if instead they kind of work against each other, if large values of one quantity above average values of one quantity are typically found with below average values of the other, well, one of those terms in the product is going to be positive, the other is going to be negative, the value for the covariance is going to be negative. So this is one way to quantify how strong that relationship is. Now, once we have the covariance between two different quantities, we can actually go back and answer a lingering question from what we had a few videos before. We know that when we're asking for the expected value of, say, a weighted sum of two random quantities, we just get to take a weighted sum of the expectations. Basically, the expectation of a sum of random quantities is the sum of the expectations, but the variance was a bit more complicated. If I wanted to know, well, what's the variance of a weighted sum of two random quantities? Well, I get to do a weighted sum of the individual variances, but I had to worry about how strongly related those two quantities were in terms of the covariance. And so now finally I can actually come up with a formula for the variance of some sort of weighted sum. So if you're in the process of building up, say, portfolios of two different stocks and you want to know what's going to be the variance of the return, well, that's going to be related to the variance of the weighted sum of the two stocks that you have in your portfolio. You need to know how strongly related those two quantities are. And so now we have that whole formula. We just need to get the covariance of the joint distribution. Now, one big problem with the covariance, though, is that its value depends on the units in which you've measured your random quantities. The covariance, if you measured your lengths in millimeters, is going to be a lot bigger than the covariance of the lengths if you measured them in meters. So, to compensate for that weakness, what we typically talk about when we are discussing how strongly associated two random variables are is the correlation, which is really just the covariance divided by the product of the standard deviations of the marginal distributions of each one of those random quantities. But if we do it this way and talk about the correlation, we're going to get a number that ranges between -1 and 1. 0 means uncorrelated. A correlation that's very close to +1 means that the association is very strong and that above average values of one random variable are almost always found with above average values of the other. A very negative correlation would mean that above average values of one would typically be found by below average values of the other. And so we can go and calculate this number to help quantify how strongly related two random quantities are once we have that joint distribution. So, for example, with our telemarketer example, we have that the conditional distribution of the number of sales given the number of calls is binomial. The number of calls, though, is random. It's given to us by a Poisson distribution. We have a formula for the joint PMF of both random quantities. If I want to know, well, how strongly related are the number of calls and the number of sales, I can go through, calculate that very special function, basically the calls minus the average number of calls times the sales minus the average number of sales times the probability of seeing that combination. And I would find that the covariance is equal to 20 in this case. If I were to simulate this, I'd come up with the same answer as well. Much easier to do with simulation. And then just converting that into the correlation by dividing by the product of the two distribution standard deviations, or just asking for core in my Monte Carlo simulation, I would find that the correlation of those two random quantities is about 0.45. If I were to go through and calculate the correlation with this joint distribution, I would actually come up with something a little bit surprising. Now, I don't want to go through and detail all of the math here. Basically, what we do have, though, is a joint distribution of x1 and x2, a formula that describes what combinations are more likely versus less likely. What we have is x1 can be anywhere between 0 and 1. x2, though, has to be within -x1 to +x1. So by definition, we do have that there is some sort of an association going on. Knowing the value of x1 narrows down what possible values of x2 I might see. If x1 is, say, 1, well, x2 can be varying over a really big range. If x1 is very close to 0, well, I know x2 is going to be really close to 0 as well. But if I go through the motions, if I go through the math and actually calculate, well, what's going to be the covariance of these two random quantities? Actually come up with that the covariance is equal to 0. So the correlation would equal to 0 as well. And so we're left scratching our heads just a little bit. How can two quantities that we know have an association with each other, the value of x2 explicitly depended on what the value of x1 was in the definition of that PDF, how do we get a covariance and a correlation of 0 out? Well, here's the rub. That correlation is really only going to measure the strength of the association between our two random quantities when we're dealing with an elliptically contoured distribution. In other words, if we were going to make a plot of the joint PDF, what we need to see is something that looks like a flattened ellipse. So going back to our joint distribution with the telemarketer example, we did see that the combinations of the number of calls and the number of sales look to be reasonably well described by a flattened ellipse. So the correlation would actually do a good job at measuring the strength of that association. If we looked at the relationship between the price of oil and the price of gas, with a scatter plot with historical data, or with the inferred distribution, we see that roughly, yeah, sure, it looks like a flattened ellipse. So the correlation would do a reasonable job of capturing the strength of that association. If instead our distribution looked like this, that 12/7 x1 times x1 plus x2, that doesn't look like a flattened ellipse at all. The correlation is of limited value here, not really designed to measure how strongly those variables are associated. And so for this example, if we make a plot of the joint distribution, we see that the shape of this is not really well described by a flattened ellipse. So we wouldn't expect the correlation to do a great job of quantifying the strength of that association. This correlation is really only designed to measure the strength of the association when that joint distribution looks like one of those flattened ellipses. So other examples where there's a very obvious association going on between our two random quantities, but the correlation to zero is as follows. So I think a good way to just think about it is that if you were to make a plot of that joint density, or if you had data, if you made a scatter plot, what you want to see is something that looks like a flattened ellipse. If there is an association between those two quantities, some obvious pattern going on, if it doesn't look like that flattened ellipse, that correlation isn't necessarily going to do a great job of quantifying the strength of that relationship. Now, what are we going to do if we have the joint distribution of, say, x1 and x2, but what we're really interested in is something more sophisticated, some transformation of those two quantities? Like, what if I wanted to know something about the distribution of x1 over x1 plus x2? Well, there's a lot of math. We're going to nope out on this.